Alright, we're back and we're doing some electrostatics. In particular, we're trying to figure out how to find electric potential for different shells of charge. And basically the picture we're going to look at is some weird thing, these sorts of pictures that we have for Gauss's law problems, where these are thin hollow shells, no thickness to worry about, no materials to worry about, they just are these thin shells that have charge. And we want to try to figure out what the potentials are for each of the three surfaces. That's our problem. Now obviously Gauss's law is something that we can use, but Gauss's law is to find electric fields. However, if we know electric fields, there's also this connection where we can integrate the field, the negative integral, and that'll tell us something about the voltage, okay, that electric potential. Now, there is something weird about potential. It's very much like gravity in mechanics, where we have to have a reference point. In gravity problems, we have to define where our height equals 0 and measure everything from that reference point. The same deal goes for voltages. It's a scalar, it's adjustable, it's arbitrary. And so we look to find out where is there a 0 point. Well, it turns out if you're doing shells, okay, spherical shells or point charges, we know generically that voltage is kq over r. And according to that expression, where is it 0? Well, it's 0 when r is at infinity, when it's far away. Okay, that's that term that we have for gravity that we see every so often. So our reference point is way out here somewhere, where we can assume there's 0 voltage, and then everything has to be measured from that point if we want to get voltages on the surfaces or at any other point in the system. So here goes. With Gauss's law, we can find out electric fields pretty quickly. We have a few different regions here, so if we're between the small one and the middle one, we can just go ahead and say with Gauss's law there's a plus 3q. If we're in this region, in between the middle and big balls, there's going to be an electric field there. Now we have a negative 2q and a 3q in that region. Okay, so between B and C, we're going to have a, let me just simplify that numerator there, just a plus q, plus 1q. And if we're outside the whole system, we have 3q, negative 2q, positive 4q, and so that's going to be a total of 5q. Okay. So if we start from infinity, if we start at our 0 voltage point, let's say we want to try to find the voltage of the outer big sphere, okay, that shell. What that would look like is we have an electric field in that region, so that's the field we have to integrate. That's going to be the 5q. It's the negative integral, and our starting point is at infinity, at 0 voltage. And then we're working our way down to the radius of r equals c, okay, that outer surface. Well, this we can do pretty quickly. We have our minus sign. 5q over 4 pi epsilon are just constants. And so really our integral is just dr over r squared. Okay? R to the minus 2 power. And that antiderivative is negative 1 over r. We have to evaluate this from infinity to c. Minus signs go away. And so the voltage of that outer shell is 5q over 4 pi epsilon. We plug in c, and then subtract what we get when we plug in infinity, but that's 0. So this is our answer. Okay, not too terrible. Well, what if we want to go to the middle ball? Okay, what if we want to find our voltage at a radius of b? Well, we have to start at infinity and work our way inwards. Okay, we have to do everything with reference to our 0 voltage, which is far away. So we have to start at infinity and go through whatever electric field there is. Okay? So we have to do what we just did. We have to go through that electric field on the outside of the system. But now the trouble is, that only goes to surface C. Once you pass inside C, now you're in a whole different region in here. There's a different electric field. Because voltages are just numbers, they're scalars, we have to add to this, working our way through this new region of electric field. We have to go from C to B, which is what we're looking for. And the field that we have there is a little bit different. Okay. Now, we already know what this first integral is. That's what we just did. I'm just going to write that answer in. But now we have to do this new integral. We have a bunch of constants. We get a negative 1 over r again. I have to evaluate from C to B this time. Okay, so the minus signs go away. Okay, so we plug in b, so we get 1 over b, and we subtract what we get with 1 over c. Now, we can actually simplify this a tad, because we have two terms that'll have a 1 over the same denominator, 1 over 4 pi epsilon c. So this will actually turn out to be a 4q over 4 pi epsilon c. And then we get another term q over 4 pi epsilon b. So this would be the voltage on that middle shell in a simplified form. Last but not least, what if we want to find the voltage on surface A, that small surface, the small shell? Well, it's got to be with reference to infinity, to our 0 voltage. We're going to work our way inwards. So we're going to have to go from infinity, but that's one electric field that goes to C. I'm not going to write the field in right now. We already know the answers to that. And then we pass through another region with a different field from C to B. That's what we just did. And then we have to add to that. Once we pass B and go inward, now we're in a different region with a different field that we have to integrate. And add that contribution. So from B to A, which is where we want to end up, and we have to plug in that field. 3Q. Okay. Well, we just wrote down the answer to these first two integrals. Okay. So we already know what that is. Let me just write those in. And now we have to put in this new contribution. Again, it's going to be negative 1 over r is our antiderivative from B going all the way to surface A. Let's see. When we do this, minus signs go away. We're going to have a 3q over 4 pi epsilon A minus another term, 3q over 4 pi epsilon B. And we can simplify just a tad. We have this 4q over 4 pi epsilon c. We have two terms with 1 over b in it, so that's going to be a plus q and a minus 3q. That's going to be minus 2q 4 pi epsilon b, and then we left this third term, 3q over 4 pi epsilon a. So this big old mess, adding all these voltages together, is what we get for that small shell. One thing to note here, this first term, if you look at that individually, that's the voltage that we'd have if we just had the outer shell. The charge is positive 4q and the radius is c. That's basically our kq over r right there. The second term, what is that? That's that middle ball. That's the voltage if that was the only thing in the picture. Negative 2q is the charge, b is the radius. And our last term, that would be the voltage you'd have if that small inner shell is all you had. Plus 3q over a. So voltages add, they're scalars. This is what we end up with. And the only other thing I'll mention here, this is also the voltage inside that small shell. Because remember, inside this small shell, if it's hollow, there is no field. There can't be any voltage difference. So the voltage inside the ball would have to be the same as on the surface of the ball in order to not have a voltage difference, to have no electric field. Okay, so that's a Faraday cage. You're safe inside there as long as your voltage is the same as the surface of the shell. Okay, so it looks messy, certainly. It takes a little bit of time to go through and do the algebra, but in the end, the key idea is we're measuring things relative to far away, relative to a zero voltage point. We're doing integrals of electric fields, where the fields are found with Gauss's law, and we're just adding voltages together as we work inwards to get the voltages on those different surfaces. So I hope this makes some sense. I hope it helps. And until next time, we'll see you later.